So this will be our last lesson on kinetics. We've already defined kinetics. Kinetics is the study of reaction rates and the factors that affect them. We know how to write and solve rate expressions. Be careful, those are the ones where you do rate is equal to -1 for reactant over coefficient times the change in concentration over the change in time equals blah, blah, blah. We've talked about the collision theory where particles must collide with enough force to overcome the activation energy, and also the particles must be oriented properly. We've started to introduce the factors that affect reaction rates, and we've talked a lot about concentration, and we said generally speaking an increase in concentration, increase in the likelihood of an effective collision, increase in reaction rate, unless of course you have zero order with respect to that reactant. Then altering that concentration will not have an effect on the reaction rate because it's not in the rate law. Remember, if something has zero order, you don't put it in the rate law. We know how to write and interpret rate laws. You saw that in the Do Now, and today we are going to continue talking about the factors that affect reaction rate. You'll see that also in your lab. And then finally, we'll learn how to draw and interpret reaction profiles showing the energy changes that occur from reactants through products. So we're going to pick up today with the factors that affect reaction rates. And I'd like to relist these here because when we get into the next chapter, we'll be talking about equilibrium, and factors that affect equilibrium are different from factors that affect reaction rates, and it can become confusing to students. So again, we're looking at the factors that affect reaction rates. And we've already talked quite a bit about concentration, and we know we can look at the effect in regard to a rate law. We're going to mention today the nature of the reactants, and that would be the most important factor. How come?
Because reactions with bond-free reagents or electron transfer occur slowly.
Well, that's something that occurs, but in regard to the nature of the reactants, what the reactants are is the most important factor, because some substances will never react with one another. So you've got it then. We'll hit that in just a minute. We'll take a look at temperature, and we've utilized this factor throughout the year. We've heated many of our reactions up. That will speed up the rate at which the reaction occurs. That's because when you increase the temperature, particles move faster. When particles move faster, you have an increase in the likelihood of an effective collision, and any factor that increases the likelihood of an effective collision will increase reaction rate. The other factor we'll take a look at is surface area. And typically we will list catalysts here as well, and we'll talk about catalysts today. So those are the factors that affect the rate at which reactions occur. We've talked about concentration already in regard to rate laws. You can also link concentration effects through reaction mechanisms. We're not going to do that at the honors level. This is a college level type concept or an AP chemistry level concept. For those of you interested, I'd be happy to work with you in smaller groups to go over reaction mechanism. It's a little tricky, but it's really not bad. We're going to pick up with those factors that affect reaction rates, and again, the nature of the reactants is the most important factor. There's a lot of information listed here, none of which I'll hold you responsible for. The bottom line is what the reactants are and whether they will react with one another is the most important factor. If you are a Boy Scout or a Girl Scout and you've ever started a fire, I'm sure that you used wood. Rubbing two rocks together, you're just not going to get a fire. Certain substances do not react with one another. We do find that if you have a lot of bond rearrangements or reactions involving electron transfer, they will occur slowly. Whereas if you have a double replacement reaction, and we've talked about those earlier in the year, they do occur much more rapidly. When you have ions of opposite charges, such as lithium ion, which is positive, and chloride ion, which is negative, those types of reactions will be a little bit faster. Earlier in the year, we looked at group 1 metals reacting with water, and we saw that as you went down the group, that is group 1 of the periodic table, those reactions became faster and faster and far more violent, and that also can affect reaction rate. Potassium's in group 1, it reacts with water very rapidly and somewhat explosively, whereas lead in group 14 doesn't react with water as fast as a group 1 metal. And I already said if you were going to make a campfire, you would want to use wood, not rocks. So what the reactants are is very important in determining whether a reaction will occur and also, in turn, reaction rate. Another factor that we want to consider is surface area. Generally speaking, as you increase surface area, you provide more sites with which an effective collision can occur. Anything that increases the likelihood of an effective collision will increase reaction rate. So you're looking for increase right there. And I'll give you 2 examples in regard to surface area. For example, let's say you went to a restaurant and you were given a drink that wasn't sweet enough for you. Maybe you got unsweetened iced tea or something like that. And you have a choice of a granulated sugar packet. So now you're looking at tiny little grains of sugar, which in this case would be sucrose. Sucrose is table sugar. And each of these little granules has surface area. Well, let's say you can use granulated sugar, or in the old days they used to have sugar cubes in a container. They don't really use that anymore. It invites bugs, never mind the lack of cleanliness. But nonetheless, if these two had the same mass, which one would dissolve faster, the granulated sugar or the sugar cube? Definitely the granulated sugar, and that's due to the fact that it has far more surface area. Each granule has surface area, where here you're just talking about the surface area, all the sides of the cube. So as you increase surface area, you provide more sites with which an effective collision can occur. Anything that increases the likelihood of an effective collision will increase reaction rate, so this substance will dissolve faster. Earlier in the year, we ran an experiment where we had zinc plus hydrochloric acid reacting to form zinc chloride and hydrogen gas. For this reaction, we used powdered zinc. How would the surface area of powdered zinc compare with a little strip of zinc metal if the masses were the same?
The powdered sugar would dissolve.
Why? Well, not dissolve, but react. But why?
Because it has less surface area.
More surface area. So this, if you look at your pen here, surface area of your pen is everywhere you can basically touch, including the bottom side. And then if you hack this pen into tiny little pieces, the surface area would be the surface area of each tiny little piece additive. So clearly that would have greater surface area. So if you grind a solid down or you generate powder from something, that will always have a greater surface area, more sites to collide effectively with, increase in reaction rate. And I've tried this experiment with both powdered zinc, and I've tried it with tiny little pieces of the metal, same mass, and this is going to react faster. So it definitely works. Also, down here, you don't really make too many fires because what's the purpose? For the most part, it's very warm down here. But up north, on Sundays during the winter, we always had a fire in the fireplace to keep our TV room warm, so when we were watching the football game, you didn't even want to get out of that warm, cozy chair. And if this is the opening of the fireplace, typically you have some type of metal structure here. And when you make a fire, you typically put a few big logs on the fire, but you don't just light it, because it's not going to stay lit. What you do when you make a fire is that you have a few big logs, and then you have what's known as kindling. So you have twigs that you've thrown on there. And then in my house, what we also did is we had crumpled up newspaper in here. So keep in mind all the little folds, increasing surface area. And then what you would do with your handy dandy little lighter is you would light all of the paper, and so this would catch on fire, this, and maybe try and get a few of the twiggies to light, and then soon the big logs would light as well. But that kindling, those little twigs, have greater surface area, and especially the crumpled up newspaper, which lights very quickly anyway if it's crumpled up, all the little nooks and crannies, and you will find that your fire lights much better this way. Same thing when you did your potato chip lab. I've done the lab with flat chips, and then I've also done the lab with those wavy chips. And I find that these chips react faster than these chips because they have greater surface area. So increase in surface area, you have more sites with which you can have an effective collision, and as a result, reaction rate increases. Temperature is another factor we want to consider. When you increase temperature, particles move faster. When particles move faster, the likelihood of an effective collision increases. This is one of the reasons why you don't drive 100 miles an hour on 95. You lose control of your car. The chance of an effective collision increases dramatically. And apparently 40 cars had flat tires today on 95 because a truck dropped a thing of nails on 95. So hope your parents weren't driving there this morning because their mood may not be great later today. In any event, as particles move faster, they're more likely to collide effectively, increase in reaction rate. We have done many experiments this year, including this one. Didn't balance that equation, sloppy. And for this particular reaction that we ran earlier in the year, we did put this on the hot plate, so we increased the temperature. Increase in temperature, the particles move faster. With an increase in speed, they were more apt to collide effectively. Increase in reaction rate. Many of the experiments we've run this year we have heated because that increases reaction rate. So these are just some of the factors that affect reaction rate, concentration, what the reactants are, temperature, and surface area. We'll talk about catalysts in a little bit. But those are the factors that affect reaction rate. So again, kinetics is the study of reaction rates and the factors that affect them. So we want to know about the factors that affect reaction rates if we're talking about kinetics. The last thing we want to talk about today are reaction profiles, and they're used to model the progress of a reaction. If you were considering this reaction here, we would want to model the energy changes that occur. Zinc and hydrochloric acid would react to form zinc chloride and hydrogen gas. We want to look at the energy changes that occur from reactants to products, and also what type of complex might exist as reactant molecules are breaking up and product molecules are forming. What you will see, and you probably learned about in middle school, is for any reaction to occur, the reactant molecules must attain some minimum amount of energy. They must attain an activation energy. And be careful, because activation energy is really an energy barrier that must be overcome for reactants to be converted to products. So it's not a minimum, if you will. You'll actually see its maximum energy really serving as an energy barrier from reactants to products forming. We are going to take a look at some profiles, and then I will help you draw these in so you don't have to draw them right from the screen. I'll draw them with you, and then we'll get them in your notes. So it says activation energy is similar to a hill that reactants must climb in order to reach products. So we're going to take a look at several profiles here. I do want to question you in one regard. We know that delta H for a reaction is equal to the sum of the delta H's of formation minus sum of delta H's of formation. And is it what minus what? Okay, good. So you have products minus reactants. When is delta H for a reaction negative? Exothermic, delta H is negative. So what's greater here if you're going to get a negative value? This has to be greater than that, right? Or you can say this is less than. So you'd have like 3 minus 6 is negative 3, so that would work. So reactants have to be greater. In contrast, if you have an endothermic reaction, delta H is positive, so now products have to be greater than reactants, correct? All right, so keep that in mind now, because we're going to link this to our reaction profiles. Looking at the following, and again, I'll help you draw this in your notes, so you really just want to pay attention and absorb right now. You've got what's known as a reaction profile showing potential energy on the Y, typically in kilojoules, and reaction coordinate or pathway on the X. And what you're looking at here is changes in potential energy from reactants to products. So your reactants would be here, and your products would be here. What's greater here, reactants or products? Reactants. So this would be an instance, let's say this is 1, and this is 5. 1 minus 5 is? Negative 4. So that would be endo or exo. So this is what an exothermic looks like, and I never memorize what's higher and what's lower. I just plug some numbers in and I can come up with it. So this would be an exothermic profile where product energy is less than that of reactant. So the delta H is from product to reactant here, and usually I draw it over here. I'll show you how I do it so you're not confused. The activation energy is the combined kinetic energy that the colliding particles must have for the reaction to occur. It's always from reactant energy to the tippy top. And you can see there that it serves as an energy barrier from reactants colliding effectively to generate products. So always from reactant to the tippy top, abbreviated EA. This profile would be exothermic. So this would be similar to trying to push a ball up to the top of the hill and hoping that it would come back over. This collision is not successful because you didn't push that ball hard enough, it got stuck and then came right back down. In contrast, this would be a successful collision, again for an exothermic reaction, where this is lower than that. How do you know this is endothermic? Product energy is higher than reactant energy, so the delta H again is from product to reactants. Be careful here because the activation energy is always from reactant to the tippy top. So that sometimes gets a little bit tricky. What you're also looking at here, and a lot of this is in your notes, we'll go through slowly, is this is a reaction that we looked at earlier in the year, where you are reacting reactant molecules together to generate product. So this one also would be exothermic. Here are your reactants. They must collide with enough force to overcome that activation energy barrier, and the molecules must be oriented properly, as we've talked about already. At the tippy top of that curve is the transition state. That is the point of maximum energy on the curve. The activated complex is the complex that shows reactant bonds breaking and product bonds forming. That activated complex is very high energy and it doesn't last long because it's very unstable. And then your products would be generated, they would be right here. And this is in your notes as well. So the transition state is the tippy top point on the curve. The activated complex represents what's happening as reactants react. Bonds are breaking, bonds are forming. You can see the bond breaking right here and the bond forming right here. Now you've got chlorine, diatomic, and nitrogen dioxide, your two products. And we can take a look at a brief clip on transition states and activation energy.
Let's analyze the changes that occur in energy and atomic arrangements as the reaction between nitric oxide and ozone occurs. Initially, the nitric oxide and ozone molecules are separated and are not reacting. The forward reaction proceeding from reactants to products is exothermic by 199.8 kilojoules per mole. Let's see how the energy changes and the molecular changes correspond. As the reactants approach, their energy increases. When the
So right there you would have your activated complex.
molecules are in a transition state or activated complex, their potential energy is at a maximum. As the transition state is passed and the molecules become more like products, the potential energy decreases. Finally, the molecules reach the energy state characteristic of the products.
And again, you can see this here as well. You can see reactant and product. So is this endo or exo? Exo. Activation energy from reactant to the tippy top. Here's your activated complex, your transition state on the curve right there, products being formed. So again, let's draw some basic diagrams so you've got it in your notes. This way you can have endo and exothermic side by side. So what we're going to do here is we will make two curves. We'll have potential energy in kilojoules. And we will have reaction pathway here and here. And let's say that the first curve I've drawn looks as such. Endo or exo?
Endo.
Endo for sure.
Will they ever be equal?
No, because then nothing's gotten done.
Good question.
It is a good question. Delta H here would be positive. Remember, the activation energy is from reactant to the tippy top. So here would be activation energy. Right here would be your transition state. R for reactants, P for products. And that would be an endothermic. In contrast, this would be an exothermic. Again, delta H here now would be negative. And activation energy is always from reactant to tippy top. So you should be able to identify endo and exo and know why. You should be able to label the activation energy as well as the delta H. Now these are very simple profiles. In more advanced kinetics, you would see it would look more like a roller coaster. And again, we already said when molecules collide, their kinetic energy is converted into potential energy. An effective collision is one in which you have an activated complex of very high energy, not going to last long, and then you will generate products. I've included this particular curve in your notes this year. I really just want you to see it because for those of you moving on next year, you'll see more of it. It's a little bit tricky. We've already said as you increase the temperature, the likelihood of an effective collision increases, and that's what's shown here. In blue is the low temperature, and red is the high temperature. Right here is your activation energy barrier, and what you can see if you're looking under the curves is far more collisions are occurring that are effective at the higher temperature. But again, this is a little bit tricky. We're not going to go there. This is already what I showed you in regard to an exothermic reaction, the transition state, the activated complex. So we've hit that already. So you want to be comfortable with endo versus exo, labeling up the curves, and I've given you several problems in your notes, in your classwork to help you do that. The last thing we really want to mention is how and why catalysts affect reaction rates. And this is very important in some drug therapies. Also, without enzymes in your body, you wouldn't be sitting here today, and why body temperature, fevers, hypothermia can be very, very dangerous. So a catalyst is a substance that increases reaction rate, but the catalyst is not consumed. You have to be able to regenerate the catalyst exactly as you started with it. Very often when you hear about catalysts or enzymes, you'll be told, oh, with a catalyst you have a lower activation energy. That is not entirely true. What the catalyst does is it provides an alternative pathway, and that alternative pathway does have a lower activation energy, so more molecules can overcome that particular barrier. For example, hydrogen peroxide will decompose to water and oxygen gas. I'm sure most of you have hydrogen peroxide at home. What color is the bottle?
Brown.
Brown. Why would you want to keep something in a brown bottle?
Because.
So it doesn't attract.
So it's not exposed to the light.
Light. So this particular reaction is light sensitive, so with more light, you'll speed up that rate. So you don't want it to decompose, otherwise it's not going to do its job. Also, you don't want to keep it under the bathroom sink, which is probably where most of you do, because it gets very hot in your bathroom as you are teenagers taking these 30-minute hot showers, which I have told my daughter is not beneficial to my water bill. You really want to store it in a cool place because increase in temperature increases reaction rate, and you don't want this to decompose. In the event you did want it to decompose, you could add manganese 4 oxide. That is a catalyst that speeds up the rate at which hydrogen peroxide decomposes by providing an alternative pathway with a lower activation energy. This is a catalyst, so it has to be recovered, and there's no change in delta H. You can see that in the panel right here. Here's a reaction profile. Is this endo or exo? Endo. Here's the uncatalyzed pathway in pink, the catalyzed pathway. No change to reactant or product energy, so delta H is the same. But you can see the catalyzed pathway has a lower activation energy. Also, hydrogen peroxide is wonderful if you ever get blood in something. Let's say you cut your arm and you ruin your favorite shirt, or when my son was about probably just shy of 3, he thought it was really fun to jump off the play structure. I didn't expect it. I had sunglasses on and I caught him, but I quickly realized that there was blood everywhere. So I wasn't really sure who was bleeding, and I realized he wasn't. So then I wiped my brow, and sure enough, my sunglasses had cut right above my eye. And so there was blood everywhere, all over one of my favorite shirts. But I remembered that hydrogen peroxide takes the blood out of everything, because I cut my arm in college, and the paramedics like, don't worry about it, hydrogen peroxide takes the blood out. So I took my shirt home, soaked it in some hydrogen peroxide, washed it, as good as new. So I always laugh when some of you text me and they're like, oh, it really works. So it does. Hydrogen peroxide takes blood out of everything. In any event, you can increase reaction rate by providing that manganese 4 oxide catalyst. Now, enzymes you learned about last year, enzymes are biological catalysts. Now, enzymes typically are proteins, and they like to work at 37 degrees Celsius, which is body temperature, 98.6. So what might happen if you have a high fever like 105? Well, why are you going to drop dead? What happens to those enzymes? They're not working properly at that higher temperature, and as a result, a lot of bodily processes will slow or shut down. Same thing with hypothermia. At very low temperatures, the enzymes don't function properly either, although sometimes they say they will cool a body to slow processes down in order to save you. And that's because the different biochemical reactions are not functioning properly at that lower temperature. Now, interestingly, a lot of drug therapy is done with inhibitors. Inhibitors are the opposite of catalysts. So inhibitors will slow a reaction rate. And this has been effectively, particularly effective with some of the drugs for HIV, the virus that causes AIDS. So what they'll do is they have designed these designer drugs that slow processes down, preventing those helper T cells from attacking themselves. And so a lot of drug therapy is with inhibitors. In the case of HIV, some of the protease inhibitors that prevent some of the processes from occurring at their typical rate, slowing them down substantially, maybe tricking them so they won't work properly, etc. So inhibitors will slow reaction rate, enzymes will speed up chemical reactions, particularly biochemical reactions if you're talking about an enzyme, since it's a biological catalyst. So a lot of what you do learn can very much affect you. Your goals today are to understand that there are factors that affect reaction rates, concentration, temperature, surface area, catalysts. Catalysts are substances that increase reaction rate by providing an alternative pathway with lower activation energies, and you should feel comfortable drawing and analyzing profiles. And if you were ever asked to show the effect of a catalyst, you would want to indicate that the catalyst has an alternative pathway with a lower activation energy, thereby increasing reaction rates because more of the particles now can overcome the activation energy. So those are your goals. Questions here?